Record right. Okay, so I'll put down time 3:02. All right, good start time. And okay, so chapter, change my camera angle here. Okay, so 28. All right, so let me come back to the problems. Let me turn this off. I don't think I'll need that here. What chapter is this? Okay, that's chapter 30, so it must be over here. Okay, so go back here to 28. 28. And it's 59. Oops, don't go too far back. 59. Oh, yeah. So in figure 59, okay, there it has. It shows a circuit. All right, so when your cable company, they, for lack of a better symbol, I'm going to say they have a signal coming out. And they send it down this coaxial cable that, usually along phone lines, goes down the back of people's yard. And of course, there's a certain distance to the cable line. And they're calling it R sub T. So there's some resistance. Then it goes off to the first subscriber, and it has to run through their house and their electronics. So we'll call that the load. And then, of course, the signal continues on down the line, because then there's probably a second subscriber. And you can kind of see the dilemma that engineers have, is that they're trying to send this signal, and then each house feeds a little bit off, and you're going to eventually run out of power. And so when do you boost it? And then, so they say, let's just say that we have a lot of subscribers. So they kind of give that ... symbol here. And so, okay, this pattern continues on. So I've drawn 1, 2, 3, 4. The book has drawn 3. And of course, then the return line on the other side of the cable does something like this. And so they're asking for the equivalent resistance. And of course, I think anybody's first reaction would be, actually, maybe I should read it here. It shows a circuit model of a transmission of electrical signals such as cable TV to a large number of subscribers. Each subscriber connects a load resistance, R sub L, between the transmission line and the ground. The ground is assumed to be zero potential and able to carry any currents, any ground connections with negligible resistance. Okay, now, the resistance of the transmission line to connect the different points of the subscriber is modeled as R sub T. Okay, so this is the resistance in the transmission line. Show that the equivalent resistance is given by this. And then they give a little helpful hint. And it's the same helpful hint that you should probably catch on to. This might be the first time, but infinities are quite fascinating, because here's what this is saying. Your first reaction might be, God, I've got so many resistors that how do I know what the heck, how many times do I need to do this? I mean, if I just had these 4, I would probably put those 2 in series, and the result of that in parallel with this, and the result of that in series with that, and then the result of that in parallel with this, and the result of that in series with that, and the result of that in parallel with that, and the result of that in series with that. And so I'd say, okay, so for these 4 subscribers, I can figure out exactly what it is. But when you have a lot of subscribers, sometimes some things interesting can happen. And so here's kind of the thought process. Go ahead and let's look at just the first subscriber. And then say something like this, that the rest of the subscribers after the first one, and so the second out to infinity, is some other value. Okay, let me not give it a name yet. Let me just say there's some value there. But here's the neat thing about infinities, because what we're trying to actually do is say, what is all the subscribers equal to? And so that's the equivalent resistance. Now, if you look at this equivalent resistance, doesn't it look like this going out, but maybe one shy?
Right.
And so the argument is if you have, and I'll exaggerate, you have millions of subscribers to your Cox cable, you take away one, and it's pretty much the same thing. 1 out of a million just doesn't change it. So here's a little trick I'm going to play. I'm trying to find what all of them are equivalent to, but I'm going to say the second to infinity is equal to equivalent. And that right here is actually easy to solve because the equivalent and the load would be in parallel. So 1 over the load plus 1 over the equivalent would be 1 over these two. Let me call it X for a moment. Because these two then would be in, okay, well, these two would be in parallel, but the result of that would be in series. So I called the equivalent of those two X. So X plus R transmission would be also equal to the equivalent. So here's what I'm going to do. I'm going to take this first equation and solve for X. So let me work that out first. I guess I'd have a common denominator of RL over R equivalent. And this would make then R equivalent plus RL equaling 1 over X. Then I'll flip it and get X equals to R load, R equivalent over R equivalent plus R load. Now I will put that into this formula, which says X, so that's R load, R equivalent over R equivalent plus R load plus R T, the transmitted, equals R equivalent. And so to solve this for R equivalent, it's going to take a little bit of math because I got an equivalent on the bottom and up on the top. So maybe I will start by getting a common denominator of R equivalent times R load. So R load, R equivalent plus, and then to get this to a common denominator, I have to multiply it by R equivalent plus R load, and that would equal to R equivalent. Now, got some more math to do. Let's see, bring this back into the picture here. I'll just write the numerator, R load, R equivalent plus R transmit, R equivalent plus R transmit, R load. So that's what I get in the numerator when I leave that alone and I do the distributive property. And if I bring this to the other side, I get R equivalent squared times R load. And I would like to solve this for R equivalence. And it looks like I have a quadratic equation. Maybe I'll write it so it looks like a quadratic equation. I will take this first term. First I'll write R load, and then I will write R equivalent squared. That's that term. Then I will take these two terms. Of course, when I move them to the other side of the equation, they become negative. And I will factor out R equivalent, so I'm left with R load plus R transmission. And then this, when I bring it over, is a negative R transmission times R load. And so if you think of this as a quadratic formula, this is AX squared plus BX plus C. Then the X would be the R equivalent equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So our b is this negative blah blah, but the negative of it makes r load plus r transmission. So there's b plus or minus.
Quick question.
Yeah.
So at this stage, I mean, you're setting this quadratic formula equal to REQ, but I look at this and I see REQ as part of. Oh wait, no. Okay, so you. Okay. I just made it. Stop. Proceed. I didn't recognize something.
Oh, okay. And then hopefully I'll get the right answer here. So the b squared would be r load plus r transmitting squared minus 4 times a. A would be r load times c, which is another minus, so I'll put a plus, r transmission, and then we got another load, so I'll square it, all over 2a, which is the load.
A question. Isn't the negative RL plus R transmission right in front? Isn't that already negative? So it'd be positive.
Oh, okay. Say that again. Where?
Back in our original equation where it's ax squared plus bx plus c, our second term, our b, is negative. So when we plug into the negative b, oh, sorry, I thought I saw a negative sign there. That's my bad. Sorry, that's equal.
Yeah, that's a equal too close together. Okay. All right.
You're not the only one who saw that. Sure.
And it doesn't look like I have the same thing quite yet. Let's see how this simplifies. Because I do have, if I kind of put this together here, this would be this over this would be 1/2. This would be a 1/2 over r transmission over r load. This then would be plus or minus. And there's, I think, some simplifying that's going to go on here. This is a square, so it'll be r load squared plus 2 r load r transmission plus RT squared plus 4 load and then transmission. And let me just focus on this.
But the R load and the last one's squared. The last term, right?
This last term and this.
Just going off of the previous line. The 4RL is squared. Yeah.
Oh, thank you. Yeah, I forgot the square there, huh?
Although...
So maybe I should look at how they wrote it. They got a transmission squared, that's good. And then they also got a 4. What happened here? Oh, well, maybe I should keep going. That's just the square root. So all of this is over. I put it inside a 4RL squared. Huh. I don't like the direction I'm going here. Let me.
I think looking at the way they did it with the key, I think they simplified it when they were actually forming the equation. I think they did it a little differently, which probably makes the math a little simpler.
Okay, let me jump over to the solution here. This was, did I write down what number this was? 50, chapter 28? 28, 59. I feel like I got either a lot of simplifying to do or I looked up something wrong. Let's see, what equation do they have? They have a oh, you know what? That's probably why I got a lot of simplifying to do. Let's take a look at this. All right. They got a slightly different. Okay, I think I got a mistake back here. Okay, so our transmission, then they got load times equivalent, and then equivalent plus load. Okay, good. Then I got a common denominator by calling it equivalent times load, equivalent times load. And so this was already L times the equivalent. And this would be the transmission times the equivalent, transmission times load, and then it would be equivalent squared load. So then I left this alone and put load times equivalent squared. And do they, let's see if they have that. Do they have, oh, shoot. No. All right, my bad. Somehow, when I went from this line to this line, I forgot to put a plus between them. There it is. So the common denominator is the equivalent plus, not times. So this is not going to be a square up there. All right, so forget this whole second page. Yeah. My bad. All right, so let me try this again. Let me just check my common denominator. So I said the common denominator would be equivalent plus the load, which means I don't have to touch anything there. So this is R load, R equivalent. And then this would be the R transmission, and then it would be those two added together. So it'd be an equivalent, and then a transmission and a load. And then over here, since it is being added, this would be R equivalent squared for the first term and R equivalent times R load for the second one. Okay, and then that load and equivalent here is the same as there. So my quadratic equation is dramatically different. It's R equivalent, and then move this over, be R transmission over R equivalent, plus, no, when I move it over, minus R transmission and R load. So when I go to do a quadratic formula, I'd go the opposite of B, so that'd be R transmission, plus or minus the square root, and B squared would be R transmission squared, minus 4 times A, which is 1, times C, which is a negative, RTRL, all over 2A. And this is looking like the answer, I think, because this right here would be a 1/2 R transmission, plus or minus 1/2. I'll just raise it to a power of 1/2 r transmitting squared plus 4r transmitting r mode. And what did they get for, now I guess I got to go back to the question. So the question they were trying to get us at was to show that we have a 1/2, in fact, in front of each of them. In fact, that's how they write it, with a 1/2. Then they have this one written first, okay, as in, yeah, okay. So, same thing. Now, they do make one thing that I didn't do, is they rule out the negative sign. As you can see, this number is always going to be bigger than that number. So if you use the negative sign, you would get a negative resistance, and that's doesn't make physical sense. So that's the extraneous root. So they drop the negative and just have the positive. So one thing they do a little different. So
Okay.
all right. Good.
What problem was that?
That was from chapter 28, so a little back, number 59.
Okay, thank you.
All right, let me switch over. Now, I don't know, Zach, did you say you had another one, or did you want to wait till?
I think it was kind of built into that, and that going through
Okay.
that actually helped. It was about how it was all set to RQ equals that,
Okay.
the Kojak formula, and after going through it, it's like, oh wait, RQ treated as X. So
Okay.
that helped.
Okay. So going to the chat room here, looks like Anthony threw one up here. Okay, and we've got chapter 27. Oh, there we go. That's a ways back. Good. You guys are getting ready for the test. If you want to go back that far, number 57. Sure. All right. So chapter 27, number 57. Time is 3:25. Okay. So let me go even further back here, 27, number 57. Okay, good, good. This is this kind of wedge shape here. Okay, so it says the material with a uniform resistivity rho is formed into a wedge as shown. Show that the resistance between the surface, the face A and the face B. Okay, so our wedge, if you will, looks maybe something like this. And to make it kind of three-dimensional, I'll do that. And I go, I guess it has an end to it, so maybe I should do that. Okay. And then they give some dimensions, like the length of the horizontal part is A, the width of it is W. And this side starts at a height of Y1, and it wedges up until it gets to a height of Y2. Okay, now what I'm going to do is think about this as slices. The reason is we know that the resistance is the resistivity times the length times the area. And we can't just apply this one equation right across the board, because the area keeps changing during the length L. So we know that this part would have lower resistance than that part. So the key is to break this down into what I would call slices, if you will. Let me just make a slice somewhere in the middle of it. And this slice, if you make it really thin, you might refer to its length as dx. So this equation, you might say, is rho dx, and it would be the area. And so the area that it has right now. Now another slice, if I maybe draw in a slightly different color, here would, of course, have a bigger area. But I guess I would still think of the formula as the same. It's just that the area is bigger. So here's what I'm going to do. I'm going to say that one little thin slice gives me a little bit of resistance dr. And one slice is adjacent to another, which is adjacent to another, so they're in series. So I know to get the total of resistance for something in series, I just take the resistor of the first one, plus the resistance of the second one, plus the resistance of the third one, dot, dot, dot. So in my case, I will be adding up the resistance of each little sheet that I'm cutting, each little slice. And I will take the limit as they get really small. So I'll just quickly jump to some calculus and say, all right, there's the idea of how I'm going to get the total resistance. So I got to do the series together with the resistivity. And once I do that with some calculus, this is how I'm going to get the answer. Okay. Now, to do this math takes a little bit of thinking, because as you can see, each slice has a different area depending on where you are. So if we make a grid, why don't we put the grid maybe back here on this corner, and the horizontal will become the x-axis. Okay. And so my first little slice actually has the smallest area, or you might say the most resistance. But as I move along the x-axis, as I'm adding up each slice, the area is coming bigger. So I need to figure out how to get this area. And you can maybe see with this blue one here, the area would be how high is it multiplied by its length, or maybe you'll call it the width, since the author gave us that as a W. So I'm just going to put down here in the denominator height times width to say, okay, that's going to be the area down here. But the reason I just wrote out the word height is because I could see that as I go along, this height is getting higher and higher. And the height would actually be the distance up to this line. Ah, a line. All right, so now I'm going to go back to my Algebra 1 class, and I remember the equation for a line. The equation for a line is y equals mx plus b, where m is the slope, x is the position, that's good, that's what I want, and b is what we call the y-intercept. So looking at this line here, which is going to be my height, I would need the slope of this line. Well, the slope is the rise over the run. So it started at y1 and finished at y2. So the rise is y2 minus y1. The run is L. The y-intercept is y1. So I'm going to use that.
What did you say the rise was?
The rise is the difference between this height at the end and this at the beginning. So
Okay,
y2
y2 minus y1. Got it. Thank you.
Mm-hmm. Okay, so I'm going to use that down here. So this becomes then an integral. And I got a dx. And in the bottom, the height is given by that equation. So this would be y2 minus y1 over L times x plus y1. Put a square bracket around that. So that's the height, and then times the W, which is the width. So that's perfect. I got an equation with an integral. It has all x's in it. Now I just got to do the math here. Now I suppose I should put my limits, and so I'm going to start right here at x equaling 0 and keep adding up until I get to x equals to L. And maybe the first thing I'll do is pull out a W in the bottom. I already got the row pulled out. But in the top, I got a dx. And ooh, now this looks like a bunch of stuff, if you will. But it actually looks like a perfect recipe for a U sub integration. So I'm going to call that whole thing, let's call U equaling to y2 minus y1 over L times x plus y1. So this just becomes a U in the bottom. Now, if I take the differential of this, I got du equals, and then it would be a y2 minus a y1 over an L times a dx. So maybe I better move to a second sheet of paper to continue on with my math. So I've got the resistivity over the width, and I've got a U downstairs, but now I can do this dx substitution. And so that would be, moving this to the other side would be L over y2 minus y1 du, when I move this over, leaving me with the dx. And then pulling out the constant L over y2 minus y1 leaves me with just an integral of U du. So that may not have been that noticeable for you at first, but that's, you know, what this was screaming at me. Do a U sub, and you got an easy integration. Although, if any of you were around in the last session, we did a tough problem, and there was a tough integral. It did not even look like a U sub, but it turned out to be one. It was interesting. But this one, anyways, this one to me looks like a U sub. The one I did last hour did not look like a U sub, but it amazingly did. But then this one would just be the ln of U when you integrate it. And then, of course, going backwards, you have ln of what U is equal to. Well, this would be y2 minus y1 over L x plus y1. That's what U is. And now that we put it back in terms of x, we could go back to our limits. See, because our limits for x, as we said back here, was from 0 to L. So 0 to L. So maybe I'll simplify these two together. And now I have an ln. And so if I put in my L here, let me do something like this for a second. So put in the L for my x. The L here for the x and the L downstairs would cancel. And so this would be a y2 minus a y1 and then plus the y1 minus ln of when I put in 0, which would be ln of y1. And of course, y1 plus and y1 minus cancel off. And so that's just ln of y2 minus ln of y1. And of course, also our properties of logarithm says we could take a subtraction and write its mathematical equivalent, which is a quotient. All right, so then I think this would finish the problem by saying that we have the resistivity times the length divided by the width, and then here's the rise of it, y2 minus y1, and then the natural log of y2 over y1. Yay! and material. Show that the resistance is, and let's see, what do they have? They got ln, y2, y1. They got an L, they got a rho. Yep, good. That's what matches.
Thank you.
So series and calculus, right? Series circuits and calculus. All right. Oh, I have a 121 question. Oh, good, good, good. All right. Let's see. Let me give you a chance to share your screen, I'm sure.
Thank you very much.
Let's see. And I think I got to change something. I think the default. Oh, no, it says one participant at a time. So I think you're okay. Go ahead.
Okay, cool.
Go.
No, it says disabled attendee screen sharing.
What? Maybe you have to go to advanced sharing. Oh yeah, it says only hosts there. Okay, so all participants, but I still want it at one at a time. Okay. All right, try that.
Okay. Yeah. So there, can you see it?
Yeah, I can see it here. Let's see. I'm just debating if I want to copy and paste. Maybe not. It looks like I can just draw that down. It says the linear density, mass per unit length of a baseball bat increases with distance x from one end of the handle according to this function. All right, let me write that down. Density is a function of x. Oh, actually, before I go too far. All right, so this is a bat problem. It sounds like I'm getting to a center of mass or rotational inertia problem, but the time is 3:39, and it's from Physics 121. Nice. All right, so the function is the density is, and you've got a 0.4 kilograms per meter plus, and then here's the slope, 1.2 times x. I won't bother to write down the units, but there's the function. Okay. Oh, it's got a nice picture of a bat. And the Dodgers just won the World Series. What could be better? Okay.
Let's go Dodgers.
So the bat has a total length. Let me kind of draw a rough picture of a bat here. And the total length is 1.02 meters. Okay.
Need that anymore?
So it's total. So its total mass is m, and its center of mass is x sub c from the handle. And I get by that we're trying to find the position of the center of mass in terms of total mass.
Yeah, what we're trying to find is the total mass and the
total mass too. Yeah.
Yeah, so we're trying to find m and xcm are the two variables that I'm looking for.
Right. Okay. All right. So here, I'm going to bump you off and grab my phone. Turn on my camera. There it goes. Okay. So I think so I wrote down the function here and kind of a rough picture of a bat. And so we're trying to find the mass of the bat and the center of mass of the bat.
Mm-hmm.
Let me start with the mass of the bat. The mass of the bat can be thought of, and I don't know if you were paying any attention to the last problem I did since it wasn't your class. But
I wasn't, unfortunately.
Okay, but in some sense, it's the same thing, that it's going to rely on some calculus. It's going to say, let's add up a bunch of pieces. So maybe just in a different color, I'm going to take this bat, and if you could imagine slicing this bat into little discs, if you will. My silly example is, if you took a carrot, you often just take the carrot and you slice it into thin pieces, all right? And the sum of all of those slices make the whole carrot. So what I'm going to do is say this. Let's say that each piece has a mass, and I'll just start here. The first slice has a mass of M1. The next one has a mass of M2. The next one has a mass of M3. The next one is M4. I think you get the idea. The total mass then would be nothing more than the sum of all these slices.
Yeah.
Okay. Now, if you think about what an integral is, an integral really is a summation of a bunch of pieces. You probably started your calculus class by doing Riemann sums, saying, okay, take this little piece plus this little piece plus this little piece plus this little piece. And if you eventually add up an infinite number of small little pieces, you get the total answer. Kind of the classic problem is you're 2 feet from a wall and you take a step towards the wall, and every time you take a step towards the wall, it's half that distance. So you go 1 foot plus a half a foot plus a quarter of a foot plus an eighth of a foot, and you get closer and closer and closer. And if you did it an infinite number of times, you might say that adds up to 2 feet. That's the total distance I would travel. So I'm going to write it like this. I'm going to say, kind of drawing on your calculus, that the total mass is a summation, and I don't know if you want to view it as a Riemann sum or as a integral. In fact, if you don't already know, this was the reason Newton loved that symbol, is he said, let's use symbol S for sum. But this is a little different sum. Why don't I stretch it? And he goes, okay, so let's call this a sum of an infinite number of pieces. All right, so that's why we use that symbol for an integration. And so I guess part of what I'm saying is a skill to build up in this class is to realize why you do integrals. You do integrals because they are the sum.
Okay.
Okay, so anytime you're adding up a bunch of things, think integral. So the problem that was the class before you, we were trying to get the total resistance of this weird shaped object. And so we had to kind of think of the object as slices and add up all of them. So we had to do an integral.
Mhm.
So that's what I'm doing here. I'm going to do an integral. All right. So I have to get the mass. Now, here is where I need to, I'll use that phrase, read the math as opposed to just doing the math, because this integral says add up all the pieces of masses. That's true. However, when you look physically at this bat and you put a grid on here, putting the handle, the problem says measure from the handle as the x-axis, you're saying, well, what I physically have to do is add up along the x-axis. And so I'm really asking this question: how could I take something that is currently listed as a dm and make it a dx? Is there anything connecting those two? And yes,
So chain
let's talk
rule
about,
in some sort of way?
and well, let's talk about density for a second.
Okay.
Density is defined as the mass per, and depending on how you want to look at it, they could give you the mass per length, or they could give you the mass per volume. This problem made it very clear that they're giving you an equation up here, which, what is the density per length? So that problem is trying to say this, that this density could be thought of as that little slice of mass divided by a little length. And if you'll let me use calculus notation, a little length on the x-axis would be written as a dx. So there's the little bit of mass, and there's the little bit of length. But that's exactly what I wanted to know. See how this equation right here is a connection between a dm and a dx?
Mm-hmm.
This means that dm would be equal to rho dx. And that's exactly what I need in this step. I can then replace dm with rho dx. And that is the big master step because they gave me the rho, and now I have something that makes sense that I can actually do. I can actually start at the handle of the bat and integrate along x. So this would be then 0.4 plus 1.2x dx. And then I would evaluate it from the handle, which is at position 0, out to the end of the barrel, which would be 1.0.
L. Yeah.
Okay, L or 1.02.
Yeah.
Yeah. So then the first term would be the 0.4. And when you integrate a constant, you get x evaluated from 0 to 1.02. And the second term would be 1.2 x squared over 2, evaluated from 0 to 1.02. And so grabbing a calculator, I would go 0.4 times 1.02 and minus 0, but that would be 0.408. I won't even write that one down. Because over here, and I might even save myself a little bit by dividing by 2, so that's a 0.6. Okay, so that's a 0.6 times x squared, 1.02 squared, minus 0. And now if I just add the 2 together, I can just go plus and then go up to that last answer, copy and paste it, and hit enter. And so it looks like we're looking at about 1.03.
Okay. And so that is my,
So that's the easier of the two.
yeah,
So that's the mass.
that's my mass.
Okay, so we go to a second page, but I'm going to play the same game of calculus here. I'm going to, though, remind you, and I guess I'm trying to think of the chapter. So I think this is chapter, must be 9, where it says to find the center of mass. We often like to use the phrase, it's a kind of a weighted average. That is, if you have, let's say, 2 objects, take the mass of the first object and the position of the first object. Add to it the mass of the second and the position of the second. And so since you're adding them together and then divide that by the total mass, in this case, adding the 2 together, or maybe just call it capital M, then this is the, as I said, a weighted average, because you're kind of taking the position and adding them together. However, the amount of mass at that position contributes. So something that is light doesn't carry as much weight to the summation as something that is heavy. Now, if you have 2 objects or 3 objects or 4 objects, it's better written this way. I'll just put the 1 over total mass and say add up let I go from 1 to however many objects you have, let's say n. And then you would take the mass of the first one times the position of the first one, and then add it to the second one, and then add it to the third one, and then add it to the fourth one, and the fifth one, and the sixth one, right? And maybe I should pause for a second. Does this formula for center mass look familiar?
Yeah.
Okay. All right, because now I'm going to make a big step here with calculus, which may or may not be completely obvious. But if I were to have an infinite number of small pieces, that's what I'm going to do here. I'm going to look at this bat as being made out of slices. And I'm going to imagine cutting them thinner and thinner and thinner. So as I cut them thinner and thinner, each slice has less mass. But then I have more slices. So I am eventually going to change then a summation. You know, if I only cut the bat into 4 pieces, then I would add up those 4 pieces. But as I cut it into smaller pieces, I eventually get an infinite number of pieces that are then 0 mass. And so let me just write it this way. I'll leave the total mass the same, but I'm going to change the summation into an integral. Maybe an intermediate step would look like this. I'm going to say, let the sum go from 1 to infinity. In the limits, as each piece gets smaller. And so as the limit, as the mass goes to 0. Now I wanted to do that intermediate step because, as you probably did at the beginning of your calculus and kind of then have kind of skipped over since then, is the definition of the integral says that when you, to go from a Riemann sum to an integral, you have to have an infinite number of pieces. And something in that piece has to go to 0. That becomes the d something. So in this case, the mass of each piece is going to 0. So I have a dm and at a position x. I think there's a big temptation in this step to call this dx, because in our math class, you always had dx. But please remember that in your math class, x did not mean the x-axis. It just meant a variable. Something was going to 0. It's not necessarily the x-axis that's going to 0. And going back to this baseball bat, when I make, say, this slice out here, when I make it thinner and thinner, I'm not saying its position is going to 0. That would be like saying its position is way over here at the handle of the bat. No. It's not the position is going to 0. It's that the mass is going to 0. And so kind of like the first half of this problem, when I put here on the screen the integral of dm, you might have been looking at that like, what is a dm? What? I'm so used to seeing things in terms of dx. Sure. But again, x in your math class did not mean position. It meant some quantity. And of course, also, I think you could be tempted to call it an x, because you know you are going to actually have to be adding up along the x-axis at some point anyway. So you know you want to get there at some point. But don't force it, in an illogical way. So I'm going to then say that what you may or may not have seen is this is the integral form of this. And so this is getting the center of mass if you have 2 pieces. This is getting the center of mass if you have 3 or 4 or 5, but they're discrete pieces. Now, if I have something that's continuous, this would be my equation. So this is the part that I was saying I'm going to have to kind of take what you've been thinking about in class and apply the calculus to get this equation before we can even do this problem.
Mm-hmm.
All right. So if that all made sense to you, it's actually pretty easy at this point, because I'm going to go back to what we did in the first part and say, hey, I have a dm, but I would like to get a dx. Is there any connection between a dx and a dm? And that is what we mean by density, the mass per unit length. And so in this first half of the problem, we substituted dm and put what it was equal to, which was rho dx. And I'm just going to do the same thing here. I'm going to then put in place of dm rho dx. And then put in the equation for the density, which was the 0.4 plus 1.2x. And then the dx. And then I'm going to integrate from 0 to 1.02. And so I suppose we could leave the symbol as just an m, but we did calculate the mass earlier on as 1.03. So I'll just put that one in right now. And then this would be 0.4. And when I do the distributive, this would be 0.4 times x. And when I integrate it, it's going to be x squared over 2, evaluated from 0 to 1.02. And this term here would be 1.2. And I have an x, but when multiplied by that x, it's x squared. So when I integrate, it's x cubed over 3, evaluated from 0 to 1.03. And again, maybe just to save me a little calculator strokes, I'll divide by 2, so that's a 0.2. And this one I'll divide by 3, so that's a 0.4. And now I'll grab the calculator. Okay, so this one here would be the 0.2 times the 1.02 squared. Here. That's that term. And this term here would be the 0.4 times 1.02. When do I put a 3 there? Maybe I was thinking about that 3. Okay. So 0.4 times 1.02, and then that's raised to a power of 3. Enter. So that would be the second term. So let me add that second one with the first, and that whole thing adds up to 0.632. Now if I divide it by the mass, I get 0.614. And the kind of, and I like the feel for that number, because the bat
gets wider at the tip, so
yeah, and it's about 1 meter long, so I would expect it to be a little bit more than halfway out.
cool. Yeah, I think that makes sense to me. I guess the thing that threw me off in the beginning was I wasn't thinking of that row of x in the front as density at all. I've been using the symbol P for momentum a bunch, so I was trying to put momentum out there, and so
yeah.
I was really confused. But once we thought about the density, it made a lot of sense.
Okay, right, yeah, and it's right. It's technically not a P. It's technically a Greek letter rho.
Yeah.
They certainly look very much the same.
Okay, cool. Thank you.
Nice. All right, good, good, good. All right, so 121 here. After those, okay, Hunter says, can we do number 61? Yeah, in chapter 28. Okay. Oh, and then Zach, you're saying the same thing. Okay, good. We got a 2-for-1 here. All right, so let me write this down. So we're going to do chapter 28, 61, and we're going to be starting here at 403 next. Okay, good. And let me switch here to 28. Okay, we were in 27. Okay, so if I scroll down, I will get to 61 eventually. Oh, good, good, good. All right, so 61 looks like this. So chapter 28, number 61. It looks like it has a battery of 9 volts and then a switch, yes, that then runs through a 12 kilo ohm resistor. At that point, it hits a node and it splits. If it goes straight down to resistor 2, they call it, it's a 15 kilo ohm. On the other hand, if it goes and continues in this loop, there is a capacitor of 10 microfarads and another resistor of 5 kilo ohms. So there's some kind of RC time constant going on here. All right, so I've got 3 resistors, 1 capacitor, a switch, a 9-volt battery. Now let me read the question here. It says, suppose the switch has been closed for a long time. Now let me pause right there. If you haven't caught this, catch it now. Something that's closed for a long time, if you remember, we started doing this way back in 26 when we first got capacitors. What they're really saying is the capacitor would build up so that it would block any more current flowing in that branch. Okay, so I know that from that phrase, this branch over here has nothing flowing. Now, it looks like it could still flow in this branch. Well, that's fine, but this branch has no current. So that's the first part I read in there. Okay, suppose the switch has been closed for a time interval significantly long for the capacitor to become fully charged. All right. Find A. And so this is why they call it steady state. It's going to remain this way forever now. Well, at least till the battery goes dead. Okay, so A, the steady state current in each of the resistors. So in A, I could just do this, that the current, in fact, I'll just kind of redraw the circuit. Switch has been closed, so I won't draw the switch. The current has to go through the 4K, and then it can't go anywhere else. That's the magical key, but to turn down and go to the 15K and go back. And so this other part, I'll call it the far right branch, is out of the picture. It's not contributing anything to the circuit. And these two then are in series because everything that goes through the 12 also goes through the 15. And because that would only be true after a long period of time. Okay. So, all right. So this could be written then as the equivalent is 27 kilo ohms. So the current would be the same in each of them. And it would be the Ohm's law, 9 volts divided by 27,000 ohms. Actually, I'll show you a little trick. It's kind of nice to write that as kilo because 9 over 27 is 1/3 and 1 over a kilo is a milli. So this is 1/3 of a milliamp. And so sometimes it's nice to leave our units in the kilo, because kilo means 1,000 when it's in the numerator, but when it's up in the denominator, it means 1,000. That's a milli. 1 over kilo is a milli. All right, so this is a third of a milliamp. So that would be the current in both of them. And so that's the easy one, I bet. That's A. What's the steady state? B says the charge Q on the capacitor. Now, let's come back to that important phrase. It's been closed for a long time. All right, so closed for a long time, again, means no current is going through here. And these two are in parallel. See, if there's no current flowing through here, then the voltage on this resistor is 0. Remember, the voltage on a resistor is its current times its resistance. And I'm saying there's no current here. So the part that is stopping the current from flowing is all the voltage on this capacitor. Now, I guess I would say that the voltage on the capacitor and the voltage on this resistor are in parallel, so they would have to add up. The voltage on these two have to be the same as the voltage on this 15 kilo ohm resistor. But as I just said, there is no voltage across this 5K because there's no current there. So what I'm trying to say is the voltage on the capacitor is the same as the voltage on the 15 kilo ohm resistor. And that's pretty easy to calculate because it is just Ohm's law, current times resistance. So I'm going to be able to figure out what the voltage is on the capacitor by realizing that it's the same as the voltage on this 15 kilo ohm resistor. So the current we just did a moment ago as 1/3 of a milliamp, and the resistance is 15 kilo ohms. And again, maybe another little mathematics here. A milli times a kilo would cancel, right? So this is 1,000ths and 1,000. And then 15 divided by 3 is 5. So 5 volts. So again, let me just say the same thing that, okay, so this is telling me that I have 5 volts on or across this 15 kilo ohm resistor, and I have argued that that would be the same as the capacitor. So now I know the voltage on the capacitor, and I know its capacitance. And so anytime you know any two of these three, you can find the third. And that's what we're asked in this problem, to find the, let me check. Yeah, find the charge. The charge Q on the capacitor. So it would be the capacitance times the voltage. So the capacitance is 10 microfarad, and the voltage we just did is 5 volts. And of course, a 10 times a 5 is a 50. And I'll just leave micro alone, but a farad is a coulomb per volt. So we have a charge of 50 microcoulombs.
Quick question on this one, just before we move on to the next part. Just looking at the key for this one, it mentions transient currents. Can I get a quick explanation of just what that definition is?
Oh, yeah, maybe I should look while they're talking about it, because right now I haven't got to any transient. So when you first close this switch, the current would come across the top, and some would go this way and some would go this way. And this would be filling up, and it would get less and less, and the current would be transitioning. And so during that time, we would call it a transitional current. And then after a period of time, it's steady state current. It reaches some constant value, which apparently is 1/3 of a milliamp here and 0 in here. So that would be the steady state. Transient, as the name implies, would be a value that would be changing a little bit with time.
All right, so transient, when it's said here, basically it's just the same as a transitioning.
Yeah.
it's changing variable. In other words.
Yeah.
Okay.
So when you first
Oh.
close the switch, you're actually going to get a lot of current because not only does it go through here, but it's got to fill this up. And then that current goes lower, lower, lower. And it doesn't take long. For these values, this would probably take under a millionth of a second. Maybe a couple, well, maybe not a million, maybe more, but definitely under a thousandth of a second. So this transient current are in time-wise small. So if you're talking about draining the battery, I would just ignore the transient current and say, look, the reason the battery drains is because of this 1/3 of a milliamp that is going on all the time, except for that first 1,000th of a second.
Okay, thanks. Appreciate that.
Okay, and so far they've only been asking me to deal with the steady state. So, but I have a feeling that they're going to talk about transient here, maybe not. All right, so C then says, oh, the switch is now opened, and then call this time equals to 0. Write the equation of the current in resistor number 2 as a function of time. Now, let me encourage you, especially, well, for both homework and for a test, to remember that we solved a discharging capacitor problem. We said if you start with a capacitor and you run it through a resistor, okay, that, yeah, we have to current or charge. Current, okay, starts off at some initial current and then decays away with an exponential, what we call the RC time constant. So, and let me go one more step. This initial current was actually then the initial voltage on this capacitor divided by the resistance you're driving it through, and then it decays. And so we solved a little differential equation to get there. And if you like, I can solve it for you again. But if you want me to, let me do it, but I'll do it after the problem, because I would suggest for this problem, you remember that, because that's exactly what is going on here. When you open this switch, you are not going to get any more current from this battery. And what's going to happen then is this capacitor, which we have said has been charged up to 5 volts or 500 microcoulombs, and it is now going to discharge itself, and that's going to be exactly like this problem, where we have a charged capacitor, and now it discharges. And so I would say, to get the answer here, we would have to say, okay, well, what voltage does it start at? Well, that was back here in part B, 5 volts. I'm going to put 5 volts. And then this is the resistance that it goes through to discharge. Now, I must say, when we derived this, we only had one resistor, but this problem looks like when it discharges, it has to go through this 15 and then also through the 5 that are in series. So you might think of this as its equivalent, which if they're in series, you add them. This is 20 kiloohms. So I'm going to put 20 kiloohms here. And so that's probably where the problem might get the hardest, is to recognize that we have an actual discharging capacitor that is only charged to 5 volts, not 9. It's tempting to say 9 because you have this 9-volt battery in the circuit, but it lost some of its voltage before it got to the capacitor across this resistor, which they don't call it number 1, but I will. Oh, wait a minute. did I write down the number wrong? Let me zoom in. I did. I wrote 5 here. This is actually a 3. Glad I looked again. Okay, so this should be an 18. 15 plus 3. Okay. And then it decays with time. And this is what we call our RC time constant. And the R, again, is the total resistance, which, again, in our case, would have to be the 18,000. So this would be the 18,000. And the capacitance is the 10 millionth. All right, so if I grab my calculator and go 5 divided by 18, that's 0.278. And I'm going to play the same little trick. A 1 over kilo is a milli, and a volt over an ohm is an amp. And then it decays away, e to the minus t over. And so what is 18,000 times 10 millionth? And that would be 0.18, which we can either leave or take the reciprocal of and put it in the numerator and write it as a negative 5.55 T. And now that I see some numbers, I said 1,000th of a second, but it's quite a bit more than that. This right here is 180 thousandths of a second. So it's about going to take about half a second before this capacitor discharges. Probably takes about that long to charge up too. So I guess I exaggerated on how quickly, but still under a second. All right, so that should be the C. I'll write the equation as a function of time. And then D, find the time interval required for the charge on the capacitor to fall to 1/5 of its value. Okay, now let's come back to this idea. This is the current in it. But also the charge on it would be the initial charge, and it followed that same pattern. In fact, if you go back to the derivation, we actually solved the equation for the charge on the capacitor, then used that to get the current in it. So this was actually solved first, and then this. But they have the same overall pattern. In fact, from charge to current is just the derivative. And you know from your, I think, your calculus classes that exponentials, when you take their derivative, e to the something just still remains as e to the something. So anytime you have a solution of e to the something, and then you have a bunch of different things, like in this case, current and charge, and they're related by a derivative or an integral, they're going to have the same pattern. So not a surprise we have the same pattern. All right, so sure enough, we have the same pattern. And so it says, how long does it take to do 1/5? Okay, so I'm not even going to bother to put in what the initial charge is, although we did solve it back in part B for 50 microcoulombs. And the reason I'm not going to bother is they say to 1/5 of its original charge. And then the original charge is going to cancel off. She's going to get 1/5, which is exactly what you get had you put in, 50 here, and 1/5 would be 10 there. And so you would go 10 divided by 50 and get 1/5. Okay. So this is 1/5. This is e to the minus t. And this R times C we did earlier as 0.18. And so now we have an equation for time. Now it's in the exponents. So we're going to have to remember our, I guess this would be algebra 2 and our logarithms. So I will take the natural log of both sides. So there's 1/5. And the whole reason of taking a natural log, because that undoes the exponent there. And so that's minus t over 0.18. And so solve this for t would mean I'd move the 0.18 and also the negative over. And so let's see how long before it has only 1/5 of its charged. And I'm pretty sure we'll be well under a second, but not as low as I originally said. All right, so I'll go a negative point, oops, I didn't do the point, negative 0.18 times a natural log of 1 divided by 5 and hit enter. And it looks like a little over 1/4 of a second, almost 1/3 of a second, 0.290 of a second. And should I check some solutions here? 28. What was it? 61. First one says, did they get a third? Oh, they got 333 microamps, which is 1/3 of a milliamp. Okay, so we got the same number. We just wrote it different. Okay, good. They got 50 microcoulombs, good. They then got an equation that looks like this, although they write it as 278 microamps. Okay, same thing. And then they write it as 290 milliseconds. Same thing. Okay, good, yay. All right, let me head back to the Zoom and see if we got some more questions here for me. That was Hunter and Zach, and then Gina. Gotta go. Thanks. For high quality solutions. You're welcome. Oh yeah, Gina always has to take off for I think work. She said one time. So good.
Do you have any last minute studying tips if no one has a question?
Well, not any different before, but I think they're worth hearing again. I think the best thing you could do is, number one, finish up all the homework if you haven't already. Getting this close, hopefully you have. And then number two, start with all these practice tests, the two from Don, and go through those solutions. Obviously, you're asking me to go through them too, but I think Don's video goes through them, and I also think, of course, the PDF has the solutions on them, which obviously, if you get lost in the solution, that doesn't help you. So I get why you're asking, but definitely do that, and then try just some other problems. You guys have a lot in the book, and you actually have two books. You got the OpenStax book, and you've got the survey book, and there's other problems certainly out there. I mean, you can just Google one here, but you're not going to have time to do every problem in the world, and that's not the point. The point is not to do every problem in the world. The point is to I'll just pick on chapter 28 here, since that's what we were working on. In 28, we had circuits that had a bunch of resistors and a bunch of capacitors and switches. So in theory, you want to be able to do any problem that had batteries and switches and resistors and capacitors. And if no capacitors were there, you're thinking, hey, Kirchhoff's laws, or if it's even a simple one that you can do the equivalency, great, just do the equivalency. If it's got a capacitor in there, then you might want to look a little closer at it. The easier one is like we just did. What happens after a long period of time? And so there's a lot of questions like that. Anyways, I'm narrowing too much on that particular type of problem, but that really sums up chapter 28. Can you do those circuits? And then of course, 28 build on 27. And so that's Ohm's law stuff. Usually students feel a little more comfortable with that compared to the magnetism at this point, as the magnetism is just hard to visualize, a lot of tough math, a lot of these right-hand rules, and of course the hardest stuff we just did. So you've only had 2 weeks for it to sink in. And so that's why I would encourage you to look at those problems, or sections 1, 2, 3, and 4. And
Okay.
of course, the other thing is don't do anything that's not necessary. So keep in mind that if you look at a problem in the back of the book and it's one related to magnetism of matter or magnetic flux, you can just skip it and say, okay, well that's for next test. I don't need to worry about that for Tuesday.
So like those 5 problems that you said are just on the next test, like don't even worry about those until.
Yeah. I wouldn't even worry about those until you feel comfortable that you're ready for the test. And so that's probably after Tuesday. And I'm going to send the same thing out Sunday. I'm going to say the lab that we do is helpful to get ready for the test. So it wouldn't be bad to do it before the test. It's a lab where we watch a charged particle, an electron in a magnetic field. And so the electron comes out and it whizzes around and it gives off a blue color. It's actually a really cool lab to see in live. I'm hoping it comes out as cool looking on video as it does in the real world. I tried to take the camera and zoom in because the experiment is literally about the size of this paper. And so on this one, I actually put the video camera in my right hand and brought it real close so it takes up the whole screen. So like you would see if you were standing right in front of it, you would get in front of it and go, cool, look at that blue light here.
That next
so it's a
week's
fun one
or
to
next
see.
Sunday's lab?
Yeah, so that's next Sunday's lab.
Okay.
And so what I'm trying to say here is the lab is going to be a judgment call on your part. It can be helpful as you are studying, but it's not as helpful as practicing other problems. So, if you practice a bunch of problems and maybe need a little break because you got brain fry, maybe you should at least just watch, maybe not even complete the lab, but watch it, learn a little bit, because it is chapter 29 stuff. It is motion of an electron in a magnetic field. And it's neat to see it actually go in a circle. I know you've already done problems with them going in a circle, but it's really cool to see them go in a circle. And again, too bad you can't do it, but I do it for you, is I put my hand on the little current knob right here. And the current knob controls some current, which makes the magnetic field. So I turn it up and down, and you'll see the circle get smaller, bigger, because one of the things we solved for was the radius of these charged particles. I guess I'll have to think about it. It would be QVB equals to MV squared over R. So if I move the R over here, it would be MV over QB. Yeah, so as I turn up the current, the magnetic field gets stronger, so the radius gets smaller. And you see this thing go into a tight circle. And then I turn the current down, and it makes a weak field, and you see it get bigger. Or I turn the speed of them up, and they go in a bigger radius like that. So, anyways, I know that's not your question, but I get excited about this lab. It's a really cool one. So like I said, I held it in my hand. So I actually did two parts. I did a board work and then I turned it off. In fact, it's not even ready. That's probably what I'll do tonight is I shot it in 4 sections. So I could either give it to you like I've been, I say part 1 of 4, part 2 of 4, part 3 of 4, or I'll put it in my computer and stitch it all together in one make video. I prefer that, but that's always a lot more work. I got to feed it in there and let the computer stitch it together. And that takes like 2 hours. So it ties up my computer for 2 hours before it stitches them all together. So that's why a lot of times I find it easier just to go, hey, here's part 1 of 3 and part 2 of 3 and part 3 of 3. Because even when it comes out of the video camera, even if I do it in all one shot, the memory size on the video camera can only hold 37 minutes. So sadly, it's an old video camera. So, but sadly, I got a new one coming. So I wonder if I will have that same problem. But sadly, when I download the videos, they're chopped into, it's actually 2 gigabytes is what it is. It comes out to be 37 minutes in high definition. And so I sometimes we'll just leave it that way. And so you'll watch, it's 37 minutes and then the next one starts. So part 2 is 37 minutes and then part 3 is maybe just 20 minutes to wrap it up. Now, by the way, the exception of that is when I do anything here on my desk, because when I do it here on my desk, I use my phone, which is, it just keeps going. I don't know how it stores it in the memory, and I don't download it separately. I just click upload to YouTube. The whole file. So if I go over 37 minutes, it just treats it as one big file. So, and that's much nicer. The lectures don't work that way, or in the labs don't, because then I couldn't use the zoom feature on the camera and the lapel mic.
So real quick, the lab videos that you have for this week, that lab is still due this Sunday, right?
So the one that is due this Sunday, coming up 2 days, is
Isn't that the inverse square magnetism?
yeah. Yes, thank you. Yeah.
Yeah, it is.
So the inverse square magnetism, and you might have done that one already. And then when the next one is coming out for Sunday and not due until the next Sunday, and that's I think what you're asking, Zach. So you don't have to do it before the test. But what I was saying is it wouldn't be bad to do it as part of your preparation for the test, because it is about chapter 29. And so that's what I was trying to say. You could use it as a preparatorial for the test. It's not as good as just doing extra hard problems, but if you get burned out on doing hard problems and still want to study, maybe that would be a good change of gears and say, all right, I'll just do the lab. So that's what I would suggest.
I just have a quick question. It's not really about any problems, but if anyone wants to go, I don't know if we have time for that, but if anyone else has something important. Cool. My question was, I'm actually going to be taking circuits next semester, and I'm also interested in like kind of just, I have a lot of circuit like work already. Like I have a lot of components basically. I was wondering if if you think it might be a good idea to go ahead and invest in like a variable power output, kind of like what you use in your labs. So I can actually try my circuits out at home, or I don't know how that's been going on due to the fact that we're not actually in person. So I'm like, I actually want to be able to test out my stuff that I make moving forward.
Right. Let me give you a couple of levels.
Mm-hmm.
One of the tricks that I used to do that I guess I'll call it old school, but it's kind of nice because it's really easy to do and really cheap. But if you're building any circuits, I would suggest just get yourself, the square batteries or the 9-volt batteries. Okay. And I'll tie this in with your circuits class because this is how the circuits class are running right now. because, as you know, we're all quarantined at home, so we don't infect each other and have a high death rate, right? And Dr. Nick, who does the circuits class, is going to require you to buy a breadboard and a bunch of resistors and a bunch of capacitors. You might already have them, and a 9-volt battery. So he runs all the labs kind of like this off 9 volts. And so maybe the first lab, you put resistor 1 and resistor 2, and maybe from that you calculate what the current is going to be, and then you actually build it. And that little kit that you're going to have to purchase comes with a really inexpensive ammeter. And so that's important. You've noticed in the lab that, I held up the ammeter and said, oh, I wish you were in lab so you could actually do the ammeter yourself. It's pretty easy, but everybody should actually do it themselves. And that's the one thing that, you guys are getting shortchanged on, I think, is like, you're not actually touching it. But in the circuits class, that is the whole class. And so you're required to buy your own. And it's kind of nice because now you'll have it. So, but
yeah, the one we have is terrible. The multimeter we have for the circuits class.
Yeah.
I mean, the fuse is broken like
it's too cheap.
5 times. Yeah, it's too cheap. If you have your own, it'd be better.
Yeah, it's got little itty bitty fuse that like breaks it.
Well, you know what I would encourage you, especially if you're going into electrical engineering. They do this at the university at UCSB. They just say, look, if this is your major, I know you may not have much money, but you need to put your money into it. It's like buying a calculator. If you're spending $100 on a calculator, you need to spend $100 on a good ammeter, a good DMM. And they make you. They don't get the cheapy ones and say, hey, get this $10 one and you'll be fine, because the $10 ones are problematic, I'll just say.
Fluke 88 is like the best of the best for
which is
Fluke 88.
Okay.
It's like a generation higher what you have in lab.
Yeah. So as you'll see in the lab, I always hold up the Flukes. We have different models, but the Fluke is our best, and so I always grab the Fluke when I can. And
that's what the auto classes use too.
Okay. And they're a bit pricey, but yeah, I would encourage you. You don't have to. I don't know if you would have to go as expensive on the Fluke, but if you got some money, do it. And so I appreciate the circuits trying to keep the cost affordable for everybody, because for some people that really is a big burden. But if there's any way, put it as a high priority. I mean, yeah. And so Preston, I would say, hey, yeah, you had to buy a cheap one, but go out and get yourself a good one if you got a little bit of money that you can put towards it. I know you probably don't have any extra disposable money that you can just waste, but this is an investment like a calculator. Anyways, what I was going to say on top of this, Hunter, is I did a lot of this when I was trying to learn circuits myself, because I didn't have a variable power supply. And so I went and I bought these things called diodes. And a diode is kind of, we like to describe it as a valve. And it just lets the current flow through. But to turn it on, it takes away about 0.7 volts. So let's say I want to build a circuit that is not 9 volts. Let's say I want to build it at, say, 5 volts. Okay, or let me do 6. 6 would be a good number, because if I put 4 of these diodes in series and then ran it through my resistors, I would be 7 times 4, that's 0.28, which is pretty close to, 2.8, which is pretty close to 3. So by the time my voltage gets to my circuit, I have lost 3 volts. So 9 minus 3 is 6. So I can now build and work with a power supply. And so here's how I would build a 6 volt power supply. Ta-da! And a lot of electronics, especially all your digital electronics, operates on 5. So if you put another one, you're not quite at 5, but you're low enough that it works. You can put another one just to see, but then it's kind of on the low side. But anyways, just run a bunch of these diodes, and you can get anything less than 9. And the other nice thing about the 9-volt batteries, the square ones, is people don't always recognize that they're designed to plug together. So now I can get from here to here, I can get 18 volts. I can put 2 9 together. Again, I remember my freshman year, we were in the dorm and we bought a box of these 9-volt batteries and we plugged them together till we had 400 volts. And then we would hook up capacitors and charge them and then walk into other people's room in the dorm and then short circuit them so they would pop and flash. And that's just, well, we thought was funny.
Sounds like a lot of fun.
What a wonderful, terrible thing to do.
Yeah. And actually later on, we learned how to build oscillators at the same frequency as the television signals. And this was before everybody was cable TV. So we'd go down the hallway with our the signal generator, and it would mess with everybody's TV. They'd be on channel 2 and we'd put it on the same frequency and it would just, their TV would turn all fuzzy and messed up, and they took a while before they knew what was going on. What? In fact, I had a fun story is I went into the lounge with it, me and my buddy, and we're all, so what are we watching? Oh, what channel is that on? They're all, I'll just say 7. Turn it to the frequency of channel 7. And they turn it on and it gets all fuzzy. And they're like, oh no. And the TV already had a history of poor reception. So somebody sitting down front gets up and they walk all the way, and right as they get to touch the TV, I turn it off and it comes back on. And they go, oh, okay, they sit down. And as soon as they sit down, I do it again. And somebody gets up, and right as they touch it, I turn it off. And this went on for about 10 times before somebody caught on that it was us two in the back laughing and screwing around with them. And then they chased us out of the room. They're probably gonna beat us up. Like, ah! Took off running. So anyway,
you could probably do that with like a phone, just streaming footage, and they'd never know.
Yeah. So anyways, I definitely digressed here, but I would encourage you, buy some extra diodes. I don't think that's part of your circuits class design. And now you can start with 9 and a couple 9-volt batteries and very, very simply get any voltage you want in terms of running a circuit. So you can try different voltages. Now, what I did too, and then if you want to take a next step, you buy these kits. And I encourage you to go to fries.com. Yeah, and they comes with a box. It comes with all the parts. You solder it all together, and it even comes with a plug. So you plug it in, and then it has a voltage output, and they're usually designed to go 0 to 35 volts, but it's kind of cool to make your own variable voltage supply. And now you can use that to learn more electronics. And that's what I did. And that was so awesome. I mean, I first bought it because, I couldn't afford the real thing, but I really wanted one. And I actually did the same thing with an oscilloscope. I bought a kit and built my own, and just the process of learning it, but it was a tool then that helped me learn even more. It was, yeah. So it was just a fun hobby.
That looks exactly like what I would like.
Okay.
Because of that.
What we're using in the circuits class is we use the potentiometer to get different voltages as well. So I don't know.
Oh, now is it a bot potentiometer? Oh,
I'm not sure.
I know what you're doing. Yeah. You're doing, well, okay. And that's not so bad. And of course your instructor is a electrical engineer, so probably knows more than me about it. But the one bad thing about that is if you go 9 volts and then you put this potentiometer here, you can reduce it down to 5 volts. But since the voltage drop depends upon how much current you have, if you then change something in your circuit, like you go from resistor 1, and then you maybe hook up a second resistor number 2, that's more current, and you won't get the same voltage drop anymore. And so you've got to readjust your potentiometer to get to 5 volts. Now, that's not so bad, especially if you have this handheld voltmeter. You could just adjust it until you're at 5 volts. That's fine. But the neat thing about diodes is when you hook up 2 or 3 of them, you drop by 0.7 regardless of how much current goes through them, as long as you don't go over their maximum. They do have a maximum where they burn out. So you do probably want to look at which ones you have and buy ones that can handle 2 or 3 amps, so that you're like, okay, I won't go above 2 or 3 amps. Just even 1 amp would be quite a bit.
What would the effect of the hooking those up in, say, parallel or series? Like, would the properties of that apply just like similar the way they do with resistors?
The diodes?
Yeah.
Well, not quite. In parallel, they're kind of boring because if you hooked it up like this, and then you hooked it to here. So let's say this is 9 volts. You would lose 0.7 here. So, but you would also lose 0.7, but they're not in series. It's just the same voltage. So you would have a power supply of 8.3. The only advantage you would get is if this coming out of this battery was, say, 2 amps, it would split and 1 amp would go this way and 1 amp would go that way. So if you had a diode that cannot handle more than 1 amp, but you still wanted to build something with 2 amps and drop the voltage by 0.7, you would do something like this.
Okay, I get it.
But again, the neat thing about diodes is you just get 0.7, whether you put a 1/2 amp, 1/3 of an amp, 1/4 of an amp. And so that's why if you're building something like this and you get, you adjust the potentiometer to eat up 4 volts, so you only have 5 volts left from your 9 volts. But then you go, okay, well, let's do the next experiment, and you hook up this. Once you do that, you're drawing more current, which goes through this resistor, which changes this drop maybe now up to a 5 volt, which now you only have 4 volts. Although then you could then turn the potentiometer down so that this goes back to 4 volts and this goes up to 5 volts. So you just have to make that adjustment before you continue on. Whereas with the diode, you know it's going to stay the same. Now, that would be the only value. So maybe that's not that much worth it. Maybe the potentiometer is just, yeah.
I mean, I've ran into problems like that. I forget to adjust it after I change the circuit, and then it's a mess. My numbers are all over.
Yeah.
I had a lot of problems last week with the potentiometer.
Okay.
Lots.
Actually, there's good and bad. The fact that you have to explain to the students that you got to readjust it actually brings up a fun discussion about circuits. And that's an educational lesson right there. However, it's not the main point of the lab. And sometimes when you get so much crazy stuff going on, it just becomes overwhelming, and then no learning goes on. That's not good either. So,
well, my main problem was I had a piece of paper like on basically on top of my breadboard to reduce the glare from my glass desk so I could see what was going on.
okay.
And the thermometer sparked and lit the paper on fire.
Well,
That's
oh,
it.
wow. I would have never thought about that. Okay. Don't hurt yourself.
Yeah, no, it was okay. But now the paper I have to turn in, I have to scan and put on my Google Drive has a hole in it. So.
Yeah, but you got a great story. Yeah, wow. You know, I had I forget now what I was doing. I don't even know why I was doing it, but I had this few years back, a 9-volt battery to do something. I think, something about a yard sale. I went by a yard sale. They were selling an old piece of electronics. It was a 9, and I wanted it, but I wouldn't want to buy an old piece of electronics that was broken, and they didn't have a battery in it. And so I think I had one in my car. So I went out and I got the battery and I put it in, and the guy said, well, the last time I tried it, it worked, which was like 20 years ago. And so I got the battery, I plugged it in, and it worked. I said, okay, I'll take this. I mean, it's a yard sale. It was like $2. I go, all right, cool. So I took it, but I took the battery out and I just dropped the battery in my pocket. And I went out and I got some change, probably at another yard sale, but I dropped the quarter, and the quarter short-circuited the battery in my pocket. The quarter must have landed just like that, because I put the quarter in my pocket and I was just standing there, and all of a sudden this burning heat was on my thigh. And I was just like, what the heck? And I reach in and I pull out the battery in the quarter, and I'm like, oh, it's hot. And I was like, whoa, that's the only thing I could figure. I go, that quarter short-circuited the battery while it was in my pocket. Wow. And it was just blistering hot. And fortunately, it's not as much energy as those lithium batteries that catch on fire. Those e-cigarette things used to be a big problem. They would short circuit inside, and they got more than hot. They caught on fire.
This is why I still don't buy Samsung phones.
Oh yeah, Samsung. Yeah, they did a mistake on their batteries for one generation there. Yeah. They tried to cut corners and cut out some of the safeguards.
Yep, they're there for a reason.
Right.
Awesome. Well, I need to head out, but I really appreciate all the information on that. I'm going to go ahead and take a look into the kits for that.
Yeah. Good.
All right.
Good.
Have a good weekend.
All right. You guys too. Work hard. Shoot me any questions you have. I'll make any set of videos that will help. I know we're working that way. So take care, everyone.
Yeah, I'm good.
All right,
I'm gonna try and finish the homework tonight, so that way tomorrow I can work on the practice tests more.
Same.
All right.
Very much the
Have
same.
a good weekend.
Bye now.
Thank you.
You are welcome.